So in the last video, I gave a very short introduction to rational functions and tried to make the argument that they're pretty similar to polynomials, what we've been learning about in the previous few sections, but just a little bit more complicated because a rational function involves two different polynomials, not just one. What a rational function is the quotient of those two polynomials. But much like polynomials, what we'll do is we'll focus on kind of some key aspects of them and come up with an approximate graph. And the first key aspect, what I want to talk about in this video, is the end behavior for a rational function. In order to understand rational function end behavior, we really need to be good with polynomial end behavior, so maybe I can give you a quick recap of what we learned in previous videos about the end behavior of polynomials. There's really four different cases to consider, and the basic idea is polynomials do all sorts of wacky, confusing stuff, loosely speaking, in the middle. But when you get far enough out to the right, the polynomial is either going to go up or it's going to go down. So what I'm getting at with these diagrams is I don't know what's going on inside the circle, all sorts of confusing polynomial stuff. But eventually, when I get far enough out to the right, this polynomial goes up forever. Similarly, this polynomial goes up forever. But these two polynomials go down forever when I go far enough out to the right. And end behavior doesn't just concern what happens when we go out to the right. It also concerns what happens when we go way out to the left. And much like when we go way out to the right, there's two different options. Either the polynomial is going to go up forever, or the polynomial is going to go down forever. And so that leaves me with these four different cases. Either it goes up in both directions, it goes up to the right and down to the left, it goes down to the right and up to the left, or it goes down to the right and down to the left. For polynomial end behavior, there's only four different cases, and maybe these crudely drawn pictures can help you understand them. So if you had a polynomial like, I don't know, y equals 3x to the 7th minus 5x to the 6th plus 11x squared minus 17x plus 1, for example, we could figure out its end behavior. And a nice characteristic of end behavior is it was completely determined by the leading term. So we can ignore all this other stuff and just focus on the 3x to the 7th. For that 3x to the 7th, we have to look for two things. First, we have to look for the leading coefficient and figure out if that's negative or positive. If we let a represent that leading coefficient, then anytime a is positive, like it is in this case, that means our polynomial is going to go up when we go to the right, as we see in each of these two pictures. And if a is negative, then our polynomial is going to go down when we go to the right, as we see in these two pictures. So if you want to figure out the behavior as the polynomial goes to the right, all you got to do is look at the leading coefficient. Positive means it goes up to the right. Negative means it goes down to the right. You're like, okay, that's one direction. What about to the left? Well, to figure out what happens when it goes to the left, what you have to do is consider the exponent, the degree of the polynomial. So the 7 in this case. And if that is an odd number, then what's going to happen is when it goes to the left, it goes in the opposite direction that it went when it went to the right. And if it's an even number, it's going to go in the same direction to the left and to the right. So in this case, we're going up both when we go to the left and to the right, therefore n must be even. Similarly, in this case, we're going in the same direction down when we go to the left and to the right. So in this picture, n is also even. However, in these two pictures, we go in opposite directions when we go left and right. In this one, we go up to the right and down to the left. In this one, we go down to the right and up to the left. Since they travel in opposite directions, that means n must be equal to some odd number. So in this specific case, we have a positive leading coefficient and an odd degree for this 3x to the 7th. So its end behavior will look like this of the four different cases. And maybe you're like, all right, that's not too bad. There's just four cases. Well, there's just four cases for polynomial end behavior, but we don't care about polynomial end behavior. We want rational function end behavior. And unfortunately, rational function end behavior is a little bit more complex than polynomial end behavior. With polynomial end behavior, you're either going to go up or down when you go to the left and to the right. With rational function end behavior, you can go up, down, or horizontal. Oh man, this is going to be super complicated. Well, it's not that bad. We're just going to have to consider more cases. The good news is the term with the highest degree is again the only one that matters. So just like this polynomial right here, for the sake of end behavior, we can completely ignore the negative 5x to the 6th and the 11x squared and all the other stuff that I have crossed out so I can't read anymore, and just focus on the 3x to the 7th. It's the same thing we're going to do with rational functions. What's more challenging is now there's two terms that have the largest degree, right? One in the numerator and one in the denominator. So what we have to do is consider three different cases. The first case is when the degree of the polynomial in the numerator is greater than the degree of the polynomial in the denominator. So in this rational function, if you focus on the polynomial in the numerator, it's an 8th degree polynomial because of this 8. And if you look at the polynomial in the denominator, it's a 3rd degree polynomial because of this 3. 8 is bigger than 3, so the degree of the top is greater than the degree of the bottom. Since I'm only concerned with end behavior, I'm only concerned with what happens when the value of x gets really large. And when the value of x gets really large, this 6x to the 8th term, loosely speaking, is going to overpower all of these other terms. So the polynomial in the numerator is going to act like just 6x to the 8th. One way you can write that mathematically is we can say as the absolute value of x heads towards infinity. In other words, when we go way to the right, if x goes towards infinity, or way to the left, if x goes towards negative infinity, in which case the absolute value of x would go towards infinity, this polynomial in the numerator is going to act like 6x to the 8th, and this polynomial in the denominator is going to act like 2x to the 3rd, so the rational function is going to act like 6x to the 8th divided by 2x to the 3rd. So maybe you're like, all right, but how do I figure out which of these 4 cases I'm in? I have 2 different leading coefficients and 2 different degrees of the polynomials. Well, what you're going to do is you're going to simplify this guy. 6x to the 8th divided by 2x cubed is just 3x to the 5th power. The 6 divided by the 2 gives me the 3, and the x to the 8th divided by x to the 3rd gives me x to the 5th. Think this is 6 times x times x times x times x times x 8 times. And this is 2 times x times x times x 3 times. And we can kind of cancel 3 of the x's from the top with 3 of the x's on the bottom. And so we're left with 5 up top. Anyways, the point is in case 1, we ignore everything except for the 2 terms that have greatest degree in the numerator and in the denominator. And then we're going to divide those 2 terms. And because the degree of the top was greater than the degree of the bottom, when we divide those 2 terms, we'll be left with a monomial. Some number times x raised up to some positive integer power. To figure out the end behavior of this rational function, all we have to do is figure out the end behavior of 3x to the 5th power. Using what we know about polynomial end behavior, we see that the leading coefficient here is positive, so it's going to go up when it goes to the right, and we see that the degree is odd, so it's going to go in opposite directions when it goes left and right. We're going to have this end behavior here. We learned in the previous section that we can write this as x heads towards negative infinity. In other words, when we go to the left on our graph, we go down. So y heads towards negative infinity. And as x heads towards positive infinity, in other words, when you go to the right on your graph, y goes up. So y heads towards positive infinity. Here's the picture that represents this end behavior. Here's the mathematical way of how you write that end behavior. But the big takeaway is just if you're in this first case, where the degree of the top is greater than the degree of the bottom, ignore everything except for the leading terms, and then divide those. And what you'll be left with will look like the first term of a polynomial that you already knew how to determine the end behavior of based on what we learned in previous videos. So if my goal was to eventually sketch the graph of this rational function, I would concede that there's a lot going on in the middle that I don't understand at all, and I'm going to have to fill this in later. But what I do know is when this graph goes out to the right, it goes up. So I have kind of an arrow pointing up in this direction. And when the graph goes out to the left, it goes down. So I got my arrow pointing in this direction. No clue what's going to happen in here yet, but we'll figure that out. All we're trying to figure out now is end behavior. And maybe you're like, all right, that's not too bad. I guess I can do this. We're just kind of reusing what we learned about end behavior for polynomials. Well, that's true if you're in case 1. But the bad news is there's not just one case. Otherwise, I wouldn't call it case 1. There's 3 different cases, so I still have to take you through the other 2 cases. And it might not surprise you that the way you figure out what case you're in will be just like the way we figured out what case we were in here. We compare the degrees of the top and the bottom. If the degree of the top is greater, we're in case 1. What if the degree of the bottom is greater than the degree of the top? So for example, if my rational function were 2x to the 3rd minus 13x squared plus x plus 2, divided by 6x to the 8th plus 9x squared minus 12x plus 20. You might recognize that the polynomial in the numerator has degree 3, and the polynomial in the denominator has degree 8. And since 8 is bigger than 3, the degree of the bottom is greater than the degree of the top, which means that I'm in case 2. How do you deal with case 2? I got great news for you. There's not 4 different options. There's only one option. Your end behavior will always be the same when you're in case 2. That's the good news. The bad news is it's new end behavior. Maybe you recall up here that I said that we can either go up, down, or horizontal. In case 2, we have this horizontal end behavior that I was talking about. Anytime the degree of the bottom is greater than the degree of the top, When we go to the left, the graph is going to get really close to a height of 0. And when we go to the right, the graph is going to get really, really close to a height of 0. I don't know what's going to happen in the middle of the graph. It's going to do all sorts of complicated stuff, but eventually it's going to settle in on a height of 0. And so my graph will look, loosely speaking, like this. I don't know if it's going to settle in on a height of 0 from the top or the bottom, so I just kind of depicted them arbitrarily. But the key point is we're not going up, we're not going down. We're getting really, really close to a height of 0, closer and closer to 0 the further you get out to the right and the further you get out to the left. All right, I guess I can just memorize that, but why does that work? Why is it the case that anytime the degree of the bottom is greater than the degree of the top, we'll always approach 0 when we go to the left and to the right? Well, the logic is kind of the same as the logic for case 1. If we're only concerned with end behavior, then the polynomial up on the top is going to act like 2x to the third when the value of x gets really, really large, either negative or positive. This negative 13x squared, this x and this 2 aren't going to matter at all. They're going to get overpowered by this 2x cubed. Similarly, this 9x squared and negative 12x and 20 aren't going to matter at all. They're going to get overpowered by this 6x to the 8th. So when my x is getting really, really large, negative or positive, this rational function is going to act like this rational function. But the nice thing about this rational function is I can simplify things here. I could cancel out my x's, and I would be left with a 1 up in the numerator and 3x to the 5th down in the denominator, because the 2 and the 6 reduce to this 3, and the x to the 3rd and the x to the 8th reduce to this x to the 5th power. Okay, but how does that help me? Well, think about what would happen here if my value of x got really, really large. I'd have some number, the number 1 in this case, divided by something that's getting really, really large. Is it really large negative or really large positive? I don't care. It doesn't matter. Any number that stays fixed divided by another number that grows without bound, whether in the negative or the positive direction, tends towards 0. Grab your calculator and take 1 and divide it by, I don't know, 99999999999. If you take a look at the result, what you'll see is you get something that's damn near 0, like 0.0000000 whatever 1. And if instead of taking that 1 and dividing by a bunch of 9s, you divide it by the negative of a bunch of 9s, you'd still get something really, really close to 0. Negative 0.000001, informally speaking. What I'm saying is anytime the degree of the bottom is greater than the degree of the top, when the value of x gets really, really large, because this rational function acts like this rational function, the end behavior here will be the same as the end behavior here. And we can picture the end behavior here because we're going to end up with the fraction where the top is not getting really large, but the bottom is getting really large. And when you take a small number and divide it by a large number, loosely speaking, you get really, really close to 0. If this is a million down here, 1 divided by a million is damn near 0, because if you have one cookie and you're dividing it amongst a million friends and you're asking yourself the question, how much cookie does each friend get? The answer is damn near 0, a crumb or whatever, a millionth of the cookie. Anyways, that's all just justification for why, in case 2, the end behavior will always look like this. Anytime the degree of the bottom is greater than the degree of the top, the graph's height will approach 0 when we go out to the left and when we go out to the right. It's worth pointing out that there's another way of stating this end behavior. It's perfectly fine to state it the way it's written here, but another way, in case you ever see it written this way, is to talk about a horizontal asymptote. We'll talk more about what a horizontal asymptote means when we actually graph these things, but I just want you to know that this sentence is synonymous with this sentence right here. It means the exact same thing. When we talk about horizontal asymptotes, we're describing end behavior. If we say there's a horizontal asymptote at y equals 0, what that means is the end behavior when we go way out to the left approaches 0, and when we go way out to the right approaches 0. That's it. Hopefully you like case 2. Case 2 is kind of the easiest of the 3 cases. We always have the same answer. All that's left for you, the student, to do is recognize that we're in case 2. But we're not done. There's 3 cases. We looked at the case where the degree of the top was bigger than the degree of the bottom. We looked at the case where the degree of the bottom was bigger than the degree of the top. But what if the 2 degrees are the exact same? Well, that's case 3. Suppose we consider this rational function, 6x cubed plus 9x squared minus 12x plus 20, divided by 2x cubed minus 13x squared plus x plus 2. You could probably do this on your own. You would probably guess that as the value of x tends towards positive infinity or negative infinity, this thing is going to act like 6x cubed divided by 2x cubed, because this 6x cubed is going to overpower all the other terms in the numerator, and this 2x cubed is going to overpower all the terms in the denominator. It's the same argument that we've done in the previous two cases. And just like in the previous two cases, we're going to simplify this thing. But this time, since the degrees of the top and the bottom are the exact same, all the x's are going to cancel out. And I'm going to be left with just a number, the number 3 in this case. 6 divided by 2 gives me this 3. This x cubed and this x cubed cancel out. What does that mean? It means that when I go way out to the left or way out to the right in my graph, the height settles in on a height of 3. In other words, there's a horizontal asymptote at y equals 3. I don't know what my graph is going to do in the middle. It's going to be really complicated. I'll figure that out in future videos. But when I get far enough out to the right, this graph is going to settle in on a height of 3. Maybe it looks like this. I don't know. You can describe the end behavior by talking about the horizontal asymptote, or you can describe the end behavior as we've been doing it. When the graph goes to the left, the y-coordinate approaches 3, and when the graph goes to the right, the y-coordinate also approaches 3. Either way is totally fine. All I want you, the student, to understand is there's 3 different cases that completely capture all of the possible end behaviors for rational functions. Case 1 is when the degree of the top is greater than the degree of the bottom. And what you do there is you take the 2 leading terms and you divide them, and that produces a monomial, and you determine the end behavior of that monomial in the same way we did with polynomials in the previous sections. Case 2 is when the degree of the bottom is greater than the degree of the top. You do the same argument where you only look at the leading terms, but now when you simplify things, you end up with a constant up top and x's down in the denominator. And what that means is that when the x gets really large, this fraction is going to be some small number divided by some large number. And when you have fractions where the top is small and the bottom is large, they get really close to 0. So in case 2, we'll always have a horizontal asymptote at 0. And then case 3, it's kind of the same idea where we only consider the leading terms of the polynomial on the top and the polynomial on the bottom. But in case 3, the degrees of those polynomials are the exact same. So when we go through and do the exact same simplification, all of the x's cancel out and we're left with just a number like the number 3. That number determines the horizontal asymptote, which tells you the end behavior. That's it. 3 cases, you understand those 3, you're good. Okay, so this is the end of the video, right? Well, almost. If you're really astute, you might have noticed that each of the 3 cases I've presented, I've given you the rational functions with the polynomials in their unfactored form. But if you remember from the intro video, typically in our class, these rational functions will be given as the quotient of 2 polynomials in their factored form. So really what you'll have to be able to do is figure out the end behavior of a rational function that looks more like what you see in this red box. You won't be given something that looks like this. You'll instead be given something that looks like this. But that's okay. We learned with polynomials how to turn something that looks like this into something that looks like this if we're only concerned with the leading term and the constant term, which is all we cared about the unfactored form for with polynomials. And it'll turn out that's all we care about the unfactored form for rational functions. What I'm saying is if somebody starts you out with this red rectangle, what you would do for the purposes of end behavior is say this is the quotient of 2 polynomials. The polynomial up top has a leading coefficient of 1x to the 3rd power, the product of this x, and this x. And the polynomial down on the bottom has a leading term of 6x to the 3rd power, the product of this x, this 2x, and this 3x. If I were to expand this thing out, I'd have a bunch more terms here that I don't care about at all, and I'd have a bunch more terms here that I don't care about at all. I don't care about them because for the purpose of figuring out end behavior, all I did was look at the leading term, so I just need to figure out these 2 guys. I guess I might as well finish this problem. At this point, you'd recognize that you have the same degree on the top and the bottom, 3 in this case. So we're in what I called case 3. And so we have a horizontal asymptote at the quotient of x cubed and 6x cubed. So 1/6 if you cancel everything out. There's a lot of confusion going on in the middle of my graph, but there's some height, 1/6, pictured somewhere in here. And if I go far enough out to the right on my graph, the graph is going to approach that height of 1/6. Same idea if I go far enough out to the left of my graph, the graph is going to approach that height of 1/6. That's everything I got on end behavior, so I'll end this video here.